Okay, good morning, everyone. This is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu. So who we have today? Today we have Dennis Allen with us and Ian Cohen. And Bill Lucas has just joined. Morning,
Hello.
guys. How y'all doing?
Fine.
So I was just looking at the physics news, and I noticed that they had an article on faster than light travel. So I was thinking we would take a look at that. Let me see if my screen sharing is working. For some reason, it's not quite working. But have you guys ever thought about whether faster than light travel is possible? What do you think, Ian? Can we ever do that?
Well, I've no problem in principle with it, Franklin, because I think the speed of light is a bit of an arbitrary speed, a bit like the speed of sound in air. It's the speed of electromagnetic radiation in the ether. There probably, or there's no reason why there aren't particles already traveling faster than the speed of light. One could call them tachyons if one wishes. And of course, I've often said that certain interactions do travel much faster than the speed of light, such as gravitational interaction. That's a bit of a hobby horse of mine.
How about you, Bill?
What that article is that you're referring to, they might be making some very specific arguments.
What about you, Bill? Do you think that faster than light travel, especially a warp drive kind of travel, would be possible?
Well, the velocity of light, c, is a reflection of the tensile strength of the electromagnetic field, as measured by William Hooper, University of California, Berkeley. And so the question is, can you have different tensile strengths of the electromagnetic field? And that's a question that I haven't seen any answers to, but it may be possible.
Well, I don't know that. See, if it was a warp drive, then you wouldn't have to change the tensile strength of space. You would just have to find your way around it. So I think in Star Trek, the idea was that the big engines in the back of the ship actually distorted space in front of the ship, such that it could travel. It wouldn't have to actually. I don't know. It created some kind of field in front of it so that the ship could pass through. Something like that.
You can talk about traveling orders of magnitude greater than the speed of light, but you can also talk about just exceeding the speed of light by a small amount, which is probably more frequently what is done. And I mean, all you have to do for the latter is change the refractive index, if you like, of the medium of space. Excuse me, so that it's just less than unity. And for example, that's what happens, as I've pointed out on a previous occasion, when electromagnetic radiation is reflected off the ionosphere. You get total internal reflection, and you actually get an exceedance of c as the phase speed of light. But only by 8% or something like that.
How about Dennis? Do you think faster than light travel is possible? Your folks at Boeing are working on that?
I've got a paper here. I don't know, can you see that? The title, it's from Galilean Electrodynamics, Relativity and Classical Physics. Let me read the abstract. The classical physics can be easily extended to produce results originally derived by Einstein's general theory of relativity, but with ordinary concepts of space and time. Is shown, and it's a typo, is shown in the concise paper written by Theodore Thornton, which is a paper I just showed you. the head theorist of NACA, which was a forerunner of NASA. In the heady days when aeronautics evolved from a very primitive art into a full-fledged science. A physicist and longtime skeptic about Einstein's theory, he sought and developed explanations to replace those involving curved space-time in abstract mathematical fields. In essence, Newton's theory is modified by only a quantum change to yield Einstein's results. We are very grateful to Muriel T. Williams for presenting us with her father's manuscript. And here it is again, if you can. It's Relativity in Classical Physics by Theodore Thornston. Galilean Electrodynamics, July-August 1995. So according to this paper, you can exceed the speed of light if you're accelerated by forces without, but you can exceed it if you're accelerated by forces from within, such as inertial propulsion forces. And I sent this paper to Godfrey, and now he's proposing that his inertial propulsion devices can exceed the speed of light by arbitrary amounts, really. And it's on page 50 of his latest work that I have anyway, Inertial Propulsion, and You Thought It's Impossible. And so if you want to read more about it, start in that book on page 50 where he claims that there's no real limit to the speed. It's just that you have to have thrust from within rather than thrust from without.
All right, so definitely think that's possible, huh?
Yes. Let me see, maybe I can quote quickly from his book, page 50. He quantizes everything like Jim Keen here. See, 50. From the logic of formula number 2, there is no logical reason for any speed limit in respect to the previous speed or the speed gain or speed magnitude, because speed gain is the difference of speeds totally independent of the speed magnitude or the amplitude or the greatness. The speed magnitude disappears in the Newtonian impulse momentum logic. It is only important in the centripetal acceleration. Accordingly, the force is the change in momentum with respect to time in a Newton straight-line motion system. Newton himself, when asked to define absolute speed limit of inertial mass motion, Newton answered, quote, "It is infinite," unquote. This is in reference to the dynamic linear formula number 2 and number 2.1.4, a correct statement. Accordingly, we must initially conclude that very likely machines propelling themselves accelerating past the speed of light might be possible, because Newton has already provided us with a cautious exception to a third law. However, when the speed limit or inertial mass question, it can be argued that if the previous speed magnitude and amplitude v0 starting at speed gain is great enough, then 1 second displacement time duration will cover the whole displacement plus distance of the universe for a very reasonable accelerated displacement distance exerted from a fixed point by a vehicular mechanism, and so on. He goes on in that vein. So yeah, he seems to be pretty much convinced that his IP devices, once they get into orbit, and they're in free fall, and they don't have to climb up through the gravity well. They go as fast as you want. They can be powered by solar cells or anything, or radioactive decay, the heat from radioactive decay. All these things are from within.
Well, he's just saying that if it was from within, that it's possible. Well, that's not really not giving us a good idea how to really do that, I suppose. They're getting a little bit of an echo here. But let's see here. This is this article that I was looking at today. You're gonna have to mute you there, Dennis, there, because we're getting quite a bit of echo out of you. So this is coming from Google News. So if you go to just searching under Google for Google Science Physics News, then you get this little tab here, and they have all kinds of articles, including this one that caught my eye this morning, which is faster than light travel. So let's go through this for a little bit and see what they have to say here. See, and this is a NASA scientist, you know, a legitimate scientist saying something about whether this is really possible. So this ain't no crackpot guy. This is actually, you know, someone who works for NASA. And they talk about the Enterprise, which is the ship capable of faster than light travel. And that's a really useful thing in science fiction because the distances between places we might want to reach would just take forever. Like we even wanted to reach our nearest star, the nearest galaxy or other star, it would take us like years because it's so far away.
So presumably, Franklin, this is in the category of orders of magnitude greater than the speed of light. It's not just exceeding it by a small amount.
Yeah, well, I think the warp factor is like the number of times you go times faster than the speed of light, or maybe that's an exponential scale.
Logarithmic.
I forget exactly. Yeah, logarithmic scale. Looks like my screen share has gone dead. For some reason, this thing just doesn't want to stay alive. Let me see if I can get this going again. Yes, for some reason. So originally, I couldn't share my screen on my own computer, and now it seems to be having some problems. Even doing this again. So let me try again. I don't know whether we can keep it going for longer than a few moments, I guess. But I think the gist of what he's saying here is that basically Einstein's relativity with space-time, that doesn't necessarily preclude that you can go faster than light. You just have to do some tricks to make it work. Exactly. Let's see. So now back to my screen share here. Okay, so what's he saying here? They're saying that, oops. They have a feasibility report saying that that the first scientific theory of warp drive, as opposed to the science fiction one, came about in 1994. And this is when theoretical physicists Miguel Hacklebreen used Einstein's theory of general relativity to develop a framework that would allow faster than light travel within the confines of the laws of physics. The key is that it makes it possible that technically the ship itself doesn't travel faster than light. So it says that there's no law of physics that says that space-time itself can't go faster than the speed of light. So this is the trick here, is that you can make space-time itself go faster. You know, I've heard this in the context of, say, the expanding universe, because if the universe is expanding and accelerating, that at some point that edge is going to be going faster than the speed of light. And they say that's okay because space itself can expand faster than the speed of light. Like, okay, so, right. So the concept is to make a ship, build it a bubble of space-time around it, and then we'll have to propel us faster than the speed of light. Similar to the idea of a race car racing on boarded train, someone standing on the tracks would see the car traveling much faster than its top speed. So I think that's kind of the science fiction picture where there's this bubble, and I guess that's the way they describe it in like they have the Enterprise, the technical diagrams and things like that. And people make up stuff like how the transporters work, and so then the cells of the Enterprise are creating a bubble around the ship, and then this bubble is what actually moves faster than the speed of light. So as long as your normal matter, I suppose, is not going faster than the speed of light, apparently the bubble can go faster than the speed of light. So what do you think of that idea? Can the bubble go faster than the speed of light, or is that just a bunch of hooey? Although I would think that is just about a good explanation as the imaginary fictional one that they came up with, basically. Right?
It's rather science fiction, I think, to me, to a certain extent. I mean, it's all possible, but it's speculation, and it's trying to show that one can exceed the speed of light and yet not contravene the accepted laws of physics, insofar as they're normally interpreted, to wit, special relativity. But to a certain extent, I reject those already, so I don't have to go into this contortion of trying to justify the possibility of faster than light travel.
What about James? What do you think of that idea that you could possibly put a bubble of space around yourself, and then you could travel faster, right? You'll have to unmute yourself there. Let's see here. Let's see. I'll unmute you myself then. Go ahead. That's it. Oops, you muted yourself again.
I'm trying to get myself unmuted here.
There you go.
I would go with the gist of what Ian just said. And I'd also add the caveat that there are different speeds of light. There's what's called the front velocity, which would be the arriving wave front, and then there's what's called the wave velocity, which would be the peak energy in the arriving wave front of light. The second point I might mention in this context is that the article apparently does not design any experiments. They prefer to talk about a TV show made into a movie series of Star Trek. Why don't they at least propose setting up some equipment to show this faster than light speed?
Well, I think as we go
now,
down
if
the
I
article,
could share my
well, the answer is that it's impossible because they don't have enough energy. See, isn't that convenient, right?
Well, if they don't have enough energy, they've sort of negated their own argument, haven't they?
Maybe. So, but you wanted to share your screen? You got something to share?
Yeah, just briefly, let me try it quickly. Let's see, share screen. Then they want me to share screen again, and then they want me to click here, and then go to there, and then I go to here. Can you see this unidirectional light speed measurement?
Let's see here. I've got your, there we go.
Unidirectional light speed measurement. Do you see the diagram?
Yeah, we
quanta
can see the
counts versus
diagram.
BMLS TIC. That's the Binary Mechanics Lab simulator. Okay. I'm just showing here that this is a unidirectional light speed. One curve going one way and the other curve going the other way in the simulated volume. So here's your front velocity where the wave front sort of arrives, the black arrow here. And here's your wave velocity. So you can start to ask which would be your peak at the waveform and or the wave packet, if you will, peak. Now, you notice over here, I've labeled faster than light. In all of these experiments which I've done, by the way, this is figure 2 in the recent paper, Light Speed Derivation. It says it in small print up here. At any rate, in all of these experiments, there's always a few bits or quanta, one state bits, which I call quanta, which arrive faster than light, quote unquote. Okay. So if here's our front velocity somewhere around here, we can project this down to the x-axis, as to where it would intersect. And you see there's a few little bits or a few little quanta arriving here before the front velocity. And there's another paper I have called Faster Than Light, which shows that there are certain mechanisms of certain configurations of quanta where you can get a slightly faster light speed in that very restricted context. But it's not orders of magnitude. I mean, it's only a few percent. And in terms of measurements that people are making to measure light speed, if they're using front velocity or wave velocity, whichever one they're using, this small little blip here may not have enough energy for the sensors used in the experiments to even detect, okay? And it's detectable, of course, in a simulation. That's sometimes the value of doing a simulation. So I'm going to stop. If there's no comment about this figure, I just wanted to define the fact that we can always ask, what light velocity are they measuring? Are they measuring the front velocity? Are they measuring the wave velocity? These are the terms in the literature. These are not my terms, okay? Which one are they measuring? Will the real light speed please stand up and raise your hand? Oftentimes they don't even say, probably because the measurement technique that they're using can't even distinguish between these two, which are quite different, as you can see here. Here is time, basically. The horizontal axis is time. And so how much time does it take for a signal to arrive? And that's measured by the quanta counts at the sensors. So I just wanted to put this up in the context of what you all were talking about, should that be of interest. I'll pause a moment in case anyone has any comment for that, and then I'll get rid of my shared screen here.
Well, just about the term, I normally use the terms wave velocity and phase velocity. Is the front velocity the same as phase velocity?
I can't, boy, phase velocity sounds awfully familiar. There's a third term which they use, which I don't think is applicable to what Ian just said, which is the trailing part of the waveform, which I've ignored in this case. But so I can't really answer that question. Probably by phase velocity. Well, I guess if they're talking about if they're being that specific in terms of which of the quote unquote aspects of the arriving wave packet they are measuring, one aspect being the so-called front velocity, or the initial arrival of quanta or energy detected by whatever system they're using experimentally, and the other being the peak, what you might call the peak, the waveform peak velocity, which I think in the literature is called wave velocity. I just tried to repeat those words so that people would be able to relate to what I'm writing about here. So I guess, Ian, I'm sorry, I can't really answer your question with regard to phase velocity.
I think in any case, whether they're the same or not, one is making a distinction between the transference of the packets and the actual way the wave is moving. Sometimes the analogy given is maybe like a snake, which is the particles of the snake are moving along the sinusoid, but the snake is also moving along the ground. So what one makes a distinction between these terms.
Yeah, that jogs my memory. I think you're exactly right about what they're referring to with phase velocity. But my point to raise is that there are different velocities or aspects of the waveform that one can measure. Which ones are being measured, and in particular experiments, do they even have the ability to distinguish between these different possible velocity measurements? Just technologically, I mean, in terms of how they're sensing whatever signals they're sending out. Now, by the way, almost all of the light speed measurements are bidirectional. They'll send a signal to a mirror, and the signal comes back, and it may bounce off many mirrors, to lengthen the path. But it's not the unidirectional light speed measurement here. So as far as my work with respect to binary mechanics, or full quantization, as I call it, this stands out as an interesting data point that these unidirectional waveforms are showing approximately the same front velocity and wave velocity, because the peaks are both the same place here at the top. In a unidirectional light speed measurement.
Actually, just thinking about it a bit further, I think the wave velocity might be constant between our two definitions, but its group, and that probably is equivalent to phase velocity, but its group velocity, I think, which might be equivalent to front velocity. The group has
probably they're probably different experimentalists and authors might use slightly different terms, which, when you look at the actual definitions, are really referring to the same thing. So I just found this wave velocity, front velocity, and wave velocity as two terms which I'm using just to link to that literature. But anyway, to get back to the original point that Franklin was making with regard to the Star Trek article, or whatever we want to call that article, my work would indicate that yes, under certain restricted conditions, and that I have a paper with this exact title I'm highlighting here with the red cursor, which shows certain configurations of quanta which can result in slightly faster light speed when those configurations occur. And as you can see, it's not a huge effect. It's a very small effect, and it confused the hell out of me, excuse my language, but it confused the hell out of me at first, because I'm saying, well, what am I measuring here? What are these, is the light speed over here the very first quanta to arrive? Right down there? If I magnify this and look there and plot just this area, you'll see that some of the quanta are arriving down here, way before this waveform, this high slope wavefront region here. So I had to work through myself what I was seeing in the simulator, and I finally came up with this, right or wrong, as they say.
So I just looked up the phase velocity in Wikipedia.
Oh, good.
And what they're saying the phase velocity is, there's a little diagram there towards the right, and you can see the the general shape of the waves as a group. And there's a little red dot, and they're showing that if you have that little red dot ride on the same part of the wave as it goes from left to right, it's going a lot faster than the green dot, which is they call the group velocity. So I don't think this is directly related to what you said there. So you can see that the waveform is moving faster than the propagation speed of the medium, I suppose. If you're looking at, where the hump is, well, where the, I don't know. I'm not exactly sure what they're tracking there, actually.
I think it's also related to dispersion, actually, because if there's zero dispersion, the phase velocity and the group velocity are equal. But when you have dispersion, that's when, for example, in this case, the phase velocity would exceed the group velocity.
Yeah, they're saying something this about it being a deep water case where the phase velocity is twice the group velocity. So there are definitely things like that. Like
and I think even in orthodox physics, the product of the two is equal to, say, what's normally c, the speed of light. So group velocity times phase velocity equals c squared. So if one is greater than c, the other has to be less than c. If you follow, that's concerned with dispersion. Yeah.
So you see, so the take-home message here is which velocity is will the real speed of light please stand up, so that we can't even begin to talk about faster than light speed necessarily without very specifically defining our terms. Now, in the illustration that
that's very true, but I think in most cases, when they talk about the speed of light, say in experiments, Michelson-Morley and that sort of thing, they mean the phase velocity.
Okay.
No, okay. I don't think they do, but
you're right. They ought to distinguish in all cases.
The difference that James was talking about would be a very small difference, a couple percent between the leading edge and when the main signal comes in. But I don't think that prevents you from saying that, well, can we go twice the speed of light? I think we could easily ask that question. Can we go twice the speed of light? And can we do that in, say, our car? That's the question. That the speed of light can go slightly faster. If you look at which parts of it, doesn't really help us. If my body wants to go faster than the speed of light. Since normally my body cannot go faster than the speed of light, basically. But we have some comments here which seem pretty interesting.
So, Franklin, when we're doing sort of like refraction experiments, we're talking about the phase velocity of light. And if we put light into a glass prism or something like that, well, the refractive index is greater than 1, and therefore the speed of light is reduced by that factor. But if we can make that refractive index less than 1, well, then the phase velocity in that medium would actually be greater than the phase velocity in vacuum, let's say. And that actually happens in the ionosphere when an electromagnetic radiation is refracted back to Earth. The refractive index is actually less than unity.
Okay, now we've got some comments here. It might be interesting to discuss. So from Jonathan Bain says, if a photon departs my nose at C, then my nose is at C relative to the photon. Thus, my nose should have infinite mass relative to the photon, making it a black hole. The photon could never leave. Well, what do people think of that? I think this shows a number of problems with relativity, I think. Foremost is that any frame of reference is valid, is I would say the first problem here. Because if it is, then yes, your nose could be said to be going at the speed of light. So now I solved that problem by saying that's simply wrong. And this is why I support an ether theory, because if you support an ether theory, then you do have a preferred frame of reference at which all speeds can be measured. So if your nose is sitting in an ether and your nose speed relative to the surrounding ether is 0, then we can observe a photon departing my nose. Only the photon would be going at c. My nose would be still 0, and then we wouldn't have these problems, right? But these problems arise because you think that your nose and your photon are equivalent. You can pick either frame of reference and make your nose end going up at the speed of light, which I think is absurd. So that's why you can't do that. You still have to have a preferred frame of reference. And I don't know about this. Let's see here. So if your nose were going at the speed of light, then it would have infinite mass, and that would make it a black hole. Well, I've never heard about that. I mean, that infinite mass would lead to a black hole. I don't know, maybe, but and then the photon could never leave because it's a black hole. So once again, we have all these problems if you think any frame of reference is as good as any other. What do you guys think? Does that sound about right to you, or do you think?
I'd like to ask a general question. My work seems to imply, both with the inertial propulsion, I talked about an absolute direction of space that might be detectable, and then with just the model of the spot cube as a cubic lattice, it seems to imply that there is an absolute frame of reference. So I'd like to ask my friends here, is there anybody out there proposing an absolute frame of reference? I'd like to look at what their work and what their work is and how they're justifying that, because that would agree with my work. And if there's nobody out there, am I the only one? I don't think I could be the only one. That's why I'm asking the question.
Well, obviously, I'm in agreement with that. Probably most physical etherists would be in agreement with that.
Well, I adopt an absolute frame of reference for analysis purposes, but it isn't identical to the ether frame. It isn't necessarily identical to the ether frame, because the ether could actually be moving relative to that absolute frame. And to get back to the comment earlier, I mean, if you look at everything from the photon's point of view, in the photon's frame of reference, well, then the universe will contract to 0 dimensions in the direction that the photon is going relative to it. Time will dilate to 0. The mass will blow up. I mean, you'll get all these absurdities. So Franklin's comment is relevant, I think. You get all these strange phenomena if you adopt the special relativity premise, and then of course the relativists have to try to justify their assumptions, which are really they blow up, they go absurd.
Well, so there's some general agreement here, if I might. There seems to be some general agreement among several bright minds here that there might well be a absolute frame of reference. Some might call it the ether. I call it, a cubic lattice, and which is not that different from what Franklin talks about also. And here we have Ian's comments. So I'd like to just push it further. If anybody in the coming time, if not right now, you come across someone who's actually trying to design an experiment to demonstrate the existence of such an absolute frame, because that would be the frame that would be used. Now, Dennis Allen shared with me a paper by, I think it was it Hill or Thorensen or
Hill Milner?
All these names. Well, that's the faster than light, but I mean the one about the pulsar time is a better time than atomic. And so you see, there are some people pushing the barriers here a little bit back, and I'd be interested in not just saying, well, we have this theoretical idea, that theoretical inclination, favoring an absolute frame of reference, but rather someone can we design an actual experiment to say we're going to go in the lab, we're going to build this equipment, forget about what the budget is, make it any budget you want. And that's going to determine pretty much yes or no, there's an absolute frame of reference, and if so, it's such and such, we can define it by the fixed hours or whatever.
Yes.
Well, I'd certainly like to see some inventive minds design such an experiment. But one could also say that the experiments have been done already, simple experiments. I mean, this is an experiment which you can repeat, and it might cost you a few dollars or a few euros. The Newton bucket experiment, which shows that certainly with regard to rotation, there's an absolute frame. Now, the only way of saving relativity is to adopt an extreme Machian principle and say, well, the universe is rotating around the bucket, and the bucket can be considered stationary. But you have to resort.
Is there a reference for that, Ian? Do you have a reference, Ian?
Yeah, I could probably give you two references. But James, if one Googles Newton's bucket, in fact, Franklin might even wish to do it now.
Okay.
Sir Isaac Newton's bucket experiment. It demonstrates because of the fluid, the bucket is half filled with water, and when it starts to rotate, the water is in contact with the bucket. But soon afterwards, you get sort of a meniscus. You get a concave meniscus. It goes up the sides. But it's not moving relative to the bucket. The bucket is moving relative to what I would consider absolute space, and Newton did as well.
Well, I've just got educated. Thank you, Ian. Thank you.
You're most welcome.
Well, because I want not just that different theoretical points of view have led us in directions, but some really convincing experiments where you can throw those out, like the bucket experiment that Ian just mentioned, and say, prove me wrong, show that I'm wrong, and if you can't do it, well, then that's tough luck for you. So, in other words, so that the idea of an absolute frame of reference is not like a fringe view within the physics community, but it's an accepted view.
I obviously don't want to stifle any views, any thinking that may lead to some more advanced experiments. I mean, that could be worthwhile. But I'd also like you to all consider this experiment and see, does it establish an absolute frame, which I think it does. The difficulty is that, as with all these experiments, the special relativists would reject what I've just said. They would say, oh no, they'd explain it away. I've forgotten all the arguments they use. But they have a number of arguments to discountenance the establishment of an absolute frame from the Newton's bucket experiment.
I'm still not sure I understand this at all. Go ahead, Dennis.
I just issued a message to Jim. Chapter 1 of J.P. Wesley Scientific Physics shows all sorts of experiments that show there's the same they all come up with basically the same absolute frame of reference, which is absolute space. And they start with Romer and Bradley's experiments, observations through a telescope. Romer's observations were known to Newton, and that's probably why he put forth the idea of absolute space, although he may not have used that term. And then Bradley came afterwards. He was an astronomer too. Romer looked at the eclipses of the moons of Jupiter, which he knew what time they would eclipse because he knew Newton's law of gravitation, and he had observed their orbits. So he could tell if there was a time delay in transmission or not. And Bradley did the same thing, only more sophisticatedly. And then there's other ones too. Let me just quickly give a list of the experiments that Wesley lists in chapter 1. Just a brief evidence for absolute space, chapter 1. The fixed star is absolute space. Absolute acceleration, Newton's second law. Classical constants of motion reveal absolute space. Absolute space comes from the anisotropy of the observed one-way velocity of light. So here it's one way. And the observations of Romer, the observations of Bradley, the Sanyo experiment, the Michelson-Gale experiment, the double shift of light from distant galaxies to detect absolute space. Baranow's coupled mirrors experiment of the absolute velocity of the closed laboratory. Baranow's tooth wheels experiment for the absolute velocity in the closed laboratory. Both of Baranow's experiments had to do with one-way velocity. And find the Muller mean determination of the velocity of the solar system using geostationary satellite data. And these all, the direction that the solar system is moving in space is about the same in all these experiments, and the direction it's moving relative to fixed stars is approximately the same in all these experiments.
Yes, in particular, Dennis's mention of the Sagnac experiment brings to mind what I was going to say. You see, most of the experiments indicating sort of an absolutivity of space are related to rotation or linear acceleration. You know, like if you're accelerating your motor car, you're pushed back in your seat, or you brake, you go forward. That seems to be absolute. And I was going to say that what is actually interesting is maybe experiments without any acceleration in a straight line, which would indicate the absolutivity of space. Now, the Sagnac experiment, which was mentioned, in my view also, and in Wesley's view, indicate the absolutivity of space. But it's a circular thing, the classic Sagnac experiment of 1913. However, Rudyong Wang, I don't know, about 20 years ago or something, did the experiment with a fiber optic conveyor, which was like a track which was moving in a straight line, and it only turned back like the end of a tank's conveyor, to go back to the detector. But it was actually a linear experiment, and that also showed the phase shift. So one could say that it's not only circular motion or indeed acceleration which indicates absolute space, although that is the easiest way of indicating it, but it can actually be indicated also by a linear velocity in a straight line.
Well, we got a comment here from Jim, and this is what he proposes as an experiment. His prediction is that if you send a spacecraft in low Earth orbit, that it will basically succeed, and that it will show the orbital velocity of the Earth. Although I think at the orbital position of GPS satellites, that still is very much showing zero velocities, as so concerned with the velocity of the Earth. I think you would have to send a satellite to the opposite side of Earth's orbit in order to actually observe the orbital speed. But I think that's kind of an experiment, James. What experiment would show that there's this fixed frame? The Michelson-Morley experiment was supposed to show that, except that when we measure the speed of the fixed frame, we find that on the Earth it's basically zero, or it's very small.
Miller did some experiments. Miller did some experiments to do better than the Michelson-Morley. He claimed that if you use that, there's two kinds of this, sidereal, and there's the other one. if you use one of the two, then you get a clear, a positive result for the velocity of light in the Michelson-Morley experiment. And
Yeah, Dayton Miller found changes occurring over like months and months. Like, winter season is different than spring season, and his experiments was like over thousands of turns of the interferometer versus the original Michelson-Morley, which, if you look at it, is a really poor experiment because he went through all this trouble to build this elaborate experiment, and he only did like 16 turns of the table. Right? Why do you do that? You don't spend like equivalent of millions of dollars just to take 16 measurements and then forget about it, right?
well, Miller did more, Franklin.
Miller did, over months, thousands.
He said that he did detect it on ether wind, but
yes,
he died, and then the guy that inherited all his scientific work was a fan of Einstein, and a lot of Miller's work disappeared.
Well, it's just that during Dayton Miller's time, when he was alive, no one could dispute him. Even Einstein said that if what Dayton Miller said is right, then, everything I just said was wrong, which it was. It's just that the relativists won the day because Dayton Miller died. So, although he never actually picked up the full velocity of the Earth, he picked up a certain fraction. And certainly he could point in the sky and say the Earth was heading that direction. And if you look at, like, we have the same idea now with the CMBR. The CMBR is telling us that the Earth is moving in like that direction from in that constellation. And it was in the same general ballpark that Dayton Miller came up with. I mean, it wasn't exact, but it came up with about the same location and speed that the Earth is going at, I think, which I think would be pretty remarkable. So the CMBR does seem to be a valid absolute frame. That's another thing. If you say, well, what's the evidence for absolute frame? Well, we definitely measure one from the CMBR. That we can measure this velocity of the Earth too. So.
The gentleman referred to as Miller's inheritor was Shanklin, and he in 1955 he wrote this comprehensive paper, I suppose trying to discountenance Miller's results, saying, there were temperature effects and he hadn't insulated the apparatus properly, and there are errors of measurements and so on. But he did seem to have a vested interest in establishing Einstein's theories and not countenancing anything that contradicted them. And it did seem that certain original papers of Miller's results, Miller's original papers, which Shanklin had custody of because he was his pupil, they did seem to disappear mysteriously. So there's a bit of a conspiracy in that he might have done away with them. I don't know.
Here are the results for Franklin. Here's the page where the results of all these experiments in Chapter 1 mentioned in Wesley are listed. I don't know if we can freeze that or let's see.
Yeah, we can kind of see some of them there. There were like 6 of them on that particular page or so. 6 or 7 maybe.
1, 2, 3, 4, 5. There's 5. Galactic redshifts, observer, Hubble, Devon, Colliers, and Peters, Rubens et al. And that showed kilometers per second, and the absolute velocities and Hubble is 300, and Devon, Colliers, and Peters is 300 plus or minus 50 kilometers per second. Rubens et al., 1976, 600 plus or minus 100 kilometers per second. 2.7 background entropy. From ground, Conklin, 1964, 200 plus or minus 100 kilometers per second. From a balloon, Henry, 320 plus 80 plus or minus 80 kilometers per second. From airplane, Smoot et al.,
Yeah, that's
1977,
okay. Well, we
300.
can look at those up a little bit later. I wanted to show another
Okay.
comment
Sure.
from Jonathan. You know, this is another problem here, which is, you know, what is the relative velocity between two photons moving in the opposite direction? You know, and this kind of begs the question of, can anything move faster than the speed of light? Because you'd think that the closing velocity here is like double the speed of light. So definitely there'd be something here said to be moving faster than the speed of light. Once again, if you can disregard the say an absolute frame and you consider one of the frames being absolute, then in this case you should see a photon heading at you at twice the speed of light, right? But once again, that wouldn't happen if you had an absolute frame of reference. If you had an absolute frame of reference, the closing velocity would still be the twice the speed of light. So there's a difference between the velocity of the light moving in its natural medium, and then there's what you might observe as the closing velocity. So I would say that the relative velocity is still twice the speed of light, but the actual physical velocity of each of those photons is still the speed of light relative to a preferred frame, is how I would answer that one. And then there's a related question, which is what is the relative velocity between two photons moving parallel to one another? And I would say the relative velocity is 0. So that's the same answer you would come up between two photons or two cars, two trains, whatever have you. The physics wouldn't matter just because it's light, I don't think. But getting back to our topic here, we got a little bit off track there talking about space. But getting back to this whole idea whether it's possible to travel faster than the speed of light. And we have this paragraph here saying that according to general relativity, the universe is a flat sheet of space-time, which is warped by an object with mass. We think of the bowling ball on a trampoline, and that bowling ball dips the trampoline down, says McDonald. And that's what mass does to space-time. The distortion of space-time is what we experience as gravity. Now, I don't know about you guys, but I think there's a whole lot of hooey. I mean, this is just BS in the worst possible way. I mean, the first problem I have with this is that this entire analogy requires gravity, right? So you have a bowling ball sheet and a trampoline and gravity, and then when you put the ball in the trampoline, it goes around. But if you were to perform this exact same experiment in a non-gravity environment, like in a space shuttle, this whole thing just doesn't work, right? So this is showing you that basically this analogy is explaining gravity by using gravity, right? Which I don't consider a valid argument. The other problem is that this is a two-dimensional example. And space is 3 dimensions. It's like, where does this ball pressing into space warp space such that it creates this downward depression, theoretically? I mean, this makes me upset, really, that anyone is willing to accept this at all. All the thing that got, once again, my point is that whole thing is just demonstrating what gravity is, right? By using gravity, right? It's not explaining what gravity is at all. That's like me taking a bowling ball, just dropping it and say that's gravity. That's no explanation at all. What do you guys think?
I accept
Well,
basically what you said there. However, to be fair, I think the main scientists would say, okay, it's a bad analogy, but that's all it is. You know, they'd say you haven't proved the thesis of general relativity by showing that this is a very poor analogy, because you have to use gravity to explain gravity. That's what they would say.
There's a new book on gravity, Franklin, which I just purchased for $5 and change using Amazon Prime and delivered it in 2 days.
Should the laws of
I should
gravitation
probably
be
recommend it.
reconsidered? No, I don't think the laws of gravity should be reconsidered. I think what needs to be considered is how it actually works.
Well,
The actual law of gravity,
got a
which is
bunch
the
of
simple, the attraction between two bodies is, mass 1 times mass 2 times the gravitational constant divided by r squared. I think that's fairly clear. So, what do you think that guy is saying in that book? Or that general relativity is a bunch of hooey?
Use a torsion pendulum or some conical pendulum or something, and you watch how it behaves during an eclipse. You find that it behaves anomalously. It doesn't behave like it should. I just continue operating as usual. And the eclipse might be, the moon might be between the sun and the earth, say. So what's happening is the gravity has to propagate through the moon before it reaches the earth. Well, if you take an electrostatic theory of gravity, and you know that, if you have a condenser, for example, a capacitor with an air gap, it has one capacitance, but if you put particles of iron, say, between say in wax, so they don't move around, then that will change the capacity. So you'd expect, if you had an electrostatic theory of gravity, that during a lunar eclipse of the sun, where the moon becomes between the Earth and the sun, since the moon is fairly large, you'd expect some anomalous behavior during the eclipse, some gravitational anomalous behavior. And this book
that's an interesting.
goes into all that. A lot of experiments with pendulums and everything.
Yeah, that's an interesting. I've never heard it really expressed that way. By the way, your microphone, we're getting a lot of noise out of it. I'm wondering whether you've got it turned up too high or something. Sometimes you get the problems with because you're getting I'm getting like popping sounds when you talk, and it's like you're overdriving the audio system. So maybe you need to turn the volume down so we don't get that. But so that would be an argument that gravity is an electrostatic effect, because that's exactly the kind of thing you might expect, that the force of gravity kind of depends upon the medium in which it's traveling across. So because the electrostatic force is sensitive to the permittivity and permeability of space, those electrostatic effects. Coulomb's law works a little bit differently when you have those things different. So, but yeah, that's interesting that when you've got the moon in the way of the sun's gravity field, that should change because of the difference in the permittivity or permeability that the sun had to travel through the moon, and that changes things a little bit. But that's interesting. But let's see here. Let's go on with our article here. So I'm saying this whole space-time thing, that's utter nonsense. There's no such thing as space and time, right? There's space and there's time. There's no such thing as space-time.
Yeah, that's a hoax. Space-time is a hoax.
Yeah, it's worse than a hoax. It just doesn't make any logical sense. But
well, curved space-time is certainly a hoax. I certainly concede that.
But, we got the NASA guy here who's saying, this is the reason we got space-time. It's like, you're talking nonsense right there.
Well, when if I may add just a brief comment, when you have articles like this, where they're taking from science fiction by the way, I like science fiction. It's a lot of fun, and sometimes maybe there's going to be an insight there. But when you have physicists writing articles based upon science fiction themes like Star Trek, you know they're bereft of any scientific thought that has any merit. You know that they have really nothing more to say, and so that's one concept.
Well, not necessarily. I mean, you have Jules Verne with his 20,000 Leagues Under the Sea, and he's clearly describing nuclear submarines and things like electric stoves, things that did not necessarily exist at the time he was writing these things. But then yet people went and they actually made these things happen.
Well,
right?
that's the positive part of science fiction. That's the plus side.
So,
but Jules Verne wasn't a physicist. He was a science fiction writer, right? So
well, I think
when you have physicists from NASA
are
talking about, well, we have to refer to Star Trek, to find something to say that might be of scientific interest, you sort of know that they've reached the end of their line. They have nothing to add.
They're just grabbing at straws here. Okay, but
they're making a pretty good living off it, though. They have nothing to add, but they're what's that?
Well, they got a nice mainstream article out of it, so that adds to their fame. For a researcher, it's publish or perish. Right?
They'll get promoted. They'll get on the tenure committee. They'll get on the salary committee. They'll get on the hiring committee. They'll get on the curriculum committee, and then they can trade favors with the other people that are on these committees to make sure that no one gets in that would upset their apple cart.
Yeah, that could be. Let's go on here. So a Cuvier drive uses the same concept. The bubble surrounding the ship is an area of space-time that is compressed in front of the ship and expanded behind it. As with gravity, you could create this distortion using a large amount of mass. Alternatively, thanks to Einstein's E equals mc squared, blah, 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 you could equally use a huge amount of energy. So let's see here. So you have to compress the space that's in front of your ship and expand it behind it. Well, that once again sounds very much like how they describe it in the science, the Star Trek guidebooks and things like that. So you would have to use a large amount of mass to compress the space in front of you. So let's see how that would work. So the Enterprise becomes this like a black hole, and it compresses the space in front of it. Now, I think that's okay. I mean, as an etherist, I think that space itself can be compressed, and that the amount you could compress it could potentially be arbitrary. I mean, it's just the amount of space between whatever ether particle you might have. In normal space, it has an equilibrium. But just like any fluid, it would be compressible. Just like on the Earth, the oceans are filled with water, which is a compressible medium, and towards the bottom of the ocean, the molecules of water are significantly closer than they are up in say, a glass of water up here on the surface, right? So I have no problem with that. So, but once you compress it, then what exactly do you do with it? You still have to go kind of through it. And the act of compressing it might make it so dense that it would make it more difficult to go through. Once again, I'm not sure how that's really helping you. But yeah, that's what they're saying here. But he says inside the bubble, time-space is completely flat, meaning the travelers wouldn't notice any strange relativistic effects. The result is that the bubble of space-time is hurled across the universe with travelers sitting comfortably inside their ship. The odometer is still reading the same number, which is potentially 0. So you would be, and I actually have no problem with that. I think the Earth is actually kind of one of these bubbles. That's why I think we don't measure any relative speed, or at least very little speed, relative to the Earth's orbit, because probably the Earth is acting like this gravitational bubble, which is trapping its own bubble of space with it, just like it captures the atmosphere. We have captured a bubble of Earth, and we don't see any, to a large extent, any emotional effects. So I have no problem with that, and I think that would certainly be a requirement for space travel, but I don't know that compressing the space in front of you and expanding it behind you is necessarily going to help you any, right? So, and this is where he says that, unfortunately, actually creating warp drive is even harder than it sounds. You have to have a very, very large amount of energy. And really, I think that that's equivalent between matter and energy is another bunch of hooey, because matter and energy are not equivalent. If you need matter to create a gravitational compression, the only thing that can do that is actually matter. I mean, what would they mean by having this energy? I mean, this is like Spock saying we're seeing this unknown energy thing out there. It's like, what the heck does that mean? It means nothing, right? So I have like a big problem with people saying that you need a very, very large amount of energy, when what you really mean is you need a very, very, very large amount of mass, right? Those two are not interchangeable in this context. Do you guys have any problem with that? It's just your hair stand up on end when people start saying that energy is equivalent to matter. I mean, they say these things like saying that the amount of matter in the universe is like only 0.00% of what it's supposed to be, but what they're really counting is the energy and how much energy is out there compared to the amount of matter. And they're always doing these little conversions in their head, and it just drives me freaking crazy. What do you think, Ian? Does that bother you as much as it bothers me, this whole conversion of matter to energy thing and just using them interchangeably, especially in this context where, clearly he says you got a whole black hole's worth of matter, and then that distorts, compresses the space in front of you. That's fine. But then you got this guy saying that, oh, well, you need infinite amount of energy to do that. That just forehead.
Well, frankly, I don't think it has concerned me quite as much as it has you, Franklin, over the years. I mean, you obviously, get quite riled at this. But I mean, I totally accept that it's an imprecise definition, to consider just a simple transference of one to the other. And also, I'm not sure about E exactly equals mc squared, in these reactions. I think it might be E equals k mc squared. So it's a shorthand way of saying, well, there's a measure of mass and there's a measure of energy, and they are proportional. So I don't quite get riled to the same extent that you do about it, Franklin. But I see that a distinction is necessary, and one should be careful of simplistic statements of that nature.
Yeah, I think that would be a good statement. This is my head-slapping statement. It's like, it's like stupid. This is like we've lost space probes because of the conversion between yards and meters, right? We lost like a Martian space probe because of that, right? And it's just really incredibly stupid. And that's it.
The other thing, by the way, just peripherally, is the populace at large think an electron volt is a tremendous amount of energy. But I mean, the charge on the electron is very, very small. It's like 1.6 times 10 to the minus 19 coulombs or something. So an electron volt is a very, very small quantity. And things like millions or billions or trillions of electron volts.
Sounds scary.
Yeah, they're still very small amounts of energy in joules. And when I was
About the
over,
amount of energy in a grain of sugar, right?
yeah, something like that. Because when I was over in Stern, we were going out to the place there where they were starting it up in 2008, I think it was. And there was a chap with a placard on the street saying, "You're going to create a black hole and you're going to destroy the universe." So he's protesting. But one of the chief directors in CERN said, "Oh, we're only producing the amount of energy that would accrue when a fly lands on a table." Which I think was probably true. I don't know what it was. It was maybe 10 to the 9 electron volts or something. You'd have to work it out. But if you multiply that by 1.6 times 10 to the minus 19, you get the charge times the voltage would equal the energy.
Yeah, they're using like the amount of energy to power a small town just to come up with the energy of a fly landing on the table. So it's rather inefficient use of energy, I'd have to say.
But like being a bit cynical, the PR advantage of talking about tera electron volts, 10 to the 12 electron volts, I mean, it sounds really tremendous. Whereas if you talked in terms of the equivalent number of joules, which might be just a pedestrian type of value, would not have the same influence on the media, the journalists.
Well, let's continue on with our article here. So this article just seems to be making, ridiculous statement upon ridiculous statement as far as I can tell. And as we go on here, we have, I think, some more ridiculous conclusions with things going on here. So next, he says, we need negative energy. See, to have deformation, you need for this kind of thing to work, you need much, much more energy than the sun or the galaxy, but it's negative energy. Okay, what the heck is negative energy? So negative energy is not something we can currently create. And how could energy be negative at all? So he says you have to consider about a particle with negative mass. And these particles react to gravity exact opposite way of particles of positive mass. Instead of being pulled towards a planet or star, they would be thrown away. Now, me personally, I don't know what this has to do with negative energy, right? That would be like just reverse gravity, not having to do with. So this is like putting two concepts together that just have nothing to do with each other at all, right? So, but he's saying basically that we would need to have, if there is some sort of component like that where we had a negative mass, whatever is keeping that mass together would be that negative energy. Yeah, negative mass. I'm not sure negative mass would react in a gravitational field as a repulsion. I mean, I've heard of people trying to think we have antimatter, and there are people who are trying to measure whether antimatter reacts to gravity the same way as regular matter. Some people predicting that it would do what he says, which is that the antimatter, the antihydrogen would go up versus down. But still not sure what that has anything to do with negative energy, right? And he said, this isn't a problem. I'll go away with refining the idea. He proved mathematically that any form of warp drive will require negative energy.
Franklin?
This makes no sense to me at all.
Franklin?
Yeah, Dennis, go ahead.
When Dave Bergman, who just died recently, and myself modeled electrons and protons, we found that we could also model negative protons and positive electrons, which are positrons, by just changing the sign of all the energy terms from plus to minus. So that's fully in accord with Paul Dirac's idea that antiparticles have negative energy, not positive energy. And ordinary particles have positive energy. And
no, I disagree. That's
well,
that's
I mean,
what I
that's
totally
what
disagree
we
with.
came up with. The model could be wrong, but it's consistent with what we've done in other things.
I mean, I would say you have positive charge and you have negative charge, and charge is charge. Charge, you can't replace the term charge with energy,
No,
which is what they seem to be doing.
Not charge. I'm talking about mass, not charge. Charge can be positive or negative, but energy terms in charge are the charge squared, which has to be non-negative. Whereas the field terms are charged without a power 2, which can be positive or negative. So there's 4 possibilities. The mass of the electron and positive energy gives you the electron, negative energy gives you the positron. And then there's a proton with positive energy, and the negative proton, same mass but negative energy. That's how it works.
Nah, that's what I'm really objecting to, is this idea that you can equivocate charge, the polarity of the charge, to energy. Now, maybe if you're doing some calculation, you might need to put the minus sign in there because of the vector, the effects of the vector math you have to do, because the effect is an attraction or opposite, right? But that's not energy. I suppose for me, energy is just matter in motion, right? And whenever you have matter and it's in motion, that's energy, right? And there's no such thing as negative energy.
The tie-in is this, that energy in electromagnetics, which Poincare claimed was everything reduced to electromagnetics ultimately, energy is obtained by integrating the Coulomb field of the particle throughout all space, inside the particle, at the surface of the particle, and outside the particle. And you get the gravitational mass, you divide the electrostatic energy throughout all space, you divide by c squared. That's gravitational mass. Now, inertial mass is the magnetic part of the energy integrated throughout all space. And so there's a Lenz's law effect, which causes inertia, which is resistance to force.
So let's see, Roger's got a comment here. So he says, the ether exists. There's a recent Royal Society lecture that admitted it. They admitted it? Oh my God. So there's a split in mainstream over those who say there is an ether versus those who don't. And, I'd say it's actually worse than that. With the admission of the Higgs field, I mean, that and them calling it a space molasses, I mean, that's their term for it. I mean, but they're still saying...
The only thing which is taboo is the term ether, as far as I can see. I didn't see that Royal Society reference, but, I mean, they talk about Higgs fields and quantum foams and God knows what. But the ether seems to be taboo. And I think I've mentioned to you recently that... a postgraduate student told me before I retired that his professor, when talking about electromagnetism, said that he actually believed in an ether, but it was as much as his job was worth to admit it. He had to keep it quiet from the authorities.
Yeah, so to keep on calling it space molasses, that's a much better idea. That's a much better idea.
The worst criticism I've ever heard from a person who was big in mainline physics was from John Lincoln from Fermilab, who admitted at some point, sort of grudgingly, that there is no mass game with relativistic velocities. It's just an appearance that can be put off to some other effect, not special relativity. And that's as far as I've ever seen any mainline person who's really in like Lincoln is. I'm actually admitting that all relativity is wrong.
Yeah, Einstein got it right when he admitted that if Dayton Miller was right, then everything he said was wrong. So
yeah.
I think he condemned himself. But any case, let's get back to our piece of complete fiction here, I would say. So we've got this concept of negative energy, right? And which I would say I would disagree with. Although apparently there's some, as Dennis points out, some people who actually think that there is negative energy. But let's see here. So he says that that more research into the fundamentals of physics is the way forward for warp drive. Yeah, let's do some actual physics instead of science fiction here. So further experimental study of naturally occurring gravitational waves and perhaps a study on trying to generate artificial gravitational waves would really advance the understanding of gravity and therefore space-time and all the connected sciences. Well, I would say that's true. I mean, first of all, we need to have a reasonable theory of what gravity is, right? And then you could create an artificial gravity environment. And then you would have a better understanding of gravity is, and therefore you would find that space-time is a complete bunch of hooey, because you would find that gravity is not due to a bending of anything. You would find that it's due to some particular force that's emanating out of mass, as we intuitively think it does, right? That's what we intuitively think it does, is that we have a lead ball, and there is something emanating out of the lead ball, which is attracting another lead ball. That's generally speaking how we think of it. And if we had charged those lead balls, like if we charged one lead ball a positive charge, another lead ball negative charge, and we would observe an attraction, we would know what's causing that. And it's very much stronger than gravity. But we would know that that's not due to any kind of space-time distortion, right? It's just an attraction, right? And I think that's what gravity ultimately is. It's just a force emanating from the masses that causes these two things to come together. Nothing to do with space-time, nothing to do with distorted, and certainly nothing to do with a bowling ball and a trampoline. That's what I would say, right? So he believes there's an even greater problem with the concept, and he's saying that there's a supersonic aircraft, and you won't hear the aircraft sound until it's gone past because the sound waves can't keep up. And the warp drive have the same problem, meaning there's no way to send a message ahead of you. Well, I don't think that's a greater problem. It's like if you've got something that's traveling faster than the speed of light, you're not going to be able to communicate with these people because your communication signal is not going to be able to catch up with you, right? So I don't know that that's a bigger problem. It's just that.
But on the other hand, he's admitting that there is a close analogy between sound transmission and light transmission. I mean, he's used the additive velocity of the light, of the sound. But I mean, relativity doesn't admit that for light. It says that the light speed will always be the same, no matter how one is traveling relative to it.
Yeah. Well, my point being is that this is like a side issue that you can't communicate. It's like, yeah, that'd be a problem, but that's not going to stop you from traveling faster than the speed of light in any way, shape, or form. But he has these other problems that if you did this, that the travelers would be bombarded with incredibly high energy radiation, which is the downfall of warp drive. Well, how can you predict that, right? Why would you be bombarded by incredibly high energy radiation? Now, presuming you could build an ether bubble around you, then I would say that whatever technology you use to do that may, in fact, shield you from anything that's coming from the outside world. I mean, theoretically, I don't know, you could fly through a sun and it wouldn't matter. If you can push space out of the way, I think you'd be able to push all the radiation out of the way as well. I mean, that radiation is just traveling in regular, normal space. And obviously, you've excluded yourself from normal space, so I don't know why that would be. But he believes that that makes warp drive completely impossible. So, but I don't think so. That's not necessarily a problem. That's not anything that you could reasonably predict based on what we know, right? Whereas this other guy, Agnew, is more optimistic, and these we rely on extensive understanding of gravity and space-time, which just isn't the case. So I would agree with him, is that you don't know enough to say what's possible and not possible. And I generally find that being the case in a lot of these dissident discussions, people ruling out things that they have no possible way of knowing whether that's true or not, right? Like people rule out the existence of an ether simply because they think that that must slow down anything going through this, defying Newton's laws, right? And it's like, well, you don't even know what that ether is. You don't even know, what the properties are. How can you declare what the properties are? You don't even know what it is, right? So, and that's exactly what this other guy is saying. Warp drive is impossible because you'd be irradiated. And it's like, well, how do you know you'd be irradiated? Or, in a similar way, how do you know that ether can't exist because it must slow things down? Well, how do you know that it must slow things down? Because I keep on pointing out things like, well, you've got things like superconductivity, and you wouldn't think that would happen, right? That's clearly electrons moving through a medium, a massive medium like a wire, and you think that would have to bump into stuff and it would have to slow down, but it doesn't, right? So once again, you can't make proclamations like that, I don't think. So there's at least one thing this guy says I can agree with, that we don't know enough to say what's possible, what isn't possible. And he says that we don't see a way with certainty that this will never happen in a million years. And so he errs on the side of scientific optimism, which I think you should do, right? Because the one way to make sure something is impossible, that something never happens, is just to say it's impossible and give up and not even try. So that's the only way to guarantee complete failure, is to not even try. So I would like to make that as kind of a certain point here. Then that's kind of one of the reasons why our group exists, because we keep on trying, right? At least we don't think that it's impossible to redescribe the space and how things work. And we're not, too beholden to the mainstream.
No, they're myth makers. They sort of morphed from being physicists to being scientific fiction people. And if you say that to them, to their face, they'll get you for it.
Yeah, I would agree with that. I mean, this particular article is science fiction, not science. I would say it's about as much science as the original Star Trek program, right? Because you're saying that, we have the warp drive, we can press the space in front of it, we expand the space behind it, and that's how it works. It's like,
it's like a Jason and the Magic Fleece or something, It ties into what they knew in those days, the Jason and the Magic Fleece, but they throw in what amounts to magic in it too, because people were superstitious in those days, and so if they wanted them to buy into their story and make them wealthy, hopefully, then they had to tell them what they wanted to hear. They had to tell them something that would interest them, not something that would agitate them, perhaps.
See, the trouble is that they won't admit that these things are possible and then leave it at that. That faster than light travel is possible and leave it at that. But it's because the conventional theories are so much against that they have to invent all this science fiction. I think in the early days of aviation, the people in the know said that supersonic flight was impossible. And they possibly gave reasons which were similar to this, because all strange things occur and all stresses occur when you exceed the speed of sound. But I mean, the same danger, I think, would accrue to people ruling out faster than light speed travel. But whether they need to go into all this science fiction or not, I think we would say that they don't. It actually vitiates their own case.
Well, I would kind of agree with that. I mean, if you're just going to go faster than the speed of light in a straightforward fashion, I think the thing that we lack is a propellant that goes faster than the speed of light, because you probably obviously can't go faster than the speed of light if you don't have something reacting out of your rocket ship that can exceed that particular speed. But theoretically, then you could break the light barrier just like you could break the sound barrier, right? But in that case, we did have something you could shove out the back of the airplane, going faster than the speed of sound, and then you can go faster than the speed of sound. It's just a matter of finding such a thing.
Inertial propulsion, Franklin. You can use inertial propulsion. That's Godfrey's argument that I read on page 50. You can use inertial propulsion, and that doesn't have the disadvantage, according to Theodore Thornton anyway, because then the argument that you can't travel faster than the speed of light goes away because forces from within, not without.
Well, I'm not sure whether, I mean, to me, that sounds like a statement of science fiction, not really supported by anything. Unfortunately, these inertial propulsion devices I've seen, they have a lot of back and forward. I mean, they're doing this basically, right? For every little bit you go forward, you have to go backwards, and they're very slow, right? So I don't know how you're going to get something that can barely going across the table, like something that can exceed this, speed of light. That just doesn't seem.
Bill Lucas tells me
plausible.
That SpaceX has under construction right now, a spaceship that has no rocketry or any engines like jet engines, but instead will go off using inertial propulsion. Will go into orbit, lift off the Earth and go into orbit, according to their plans anyway. And they must have built prototypes, or they wouldn't have spent all that money under construction.
Yeah, I gotta really doubt that. I'm pretty sure, because SpaceX's factory is a gigantic open space, and the only thing you see in there are big tubes and rockets. So I don't know that they could have had another project going on that could be like that. That's just got to be one of those things that Bill's saying that we can't confirm.
Bill says that he can gets emails from SpaceX. He somehow figured out a way to get on their email list, and they claim out and out that they've got this ship under construction. And it's no rockets, no jet engines, no propellers, just inertial propulsion. And but I'm not computer savvy enough to bring it up myself. I don't know how to do that sort of thing. But certainly I was hoping I could talk you into look and check into that one way or the other.
Well, in stories like this whole crystal energy thing, I mean, when I tracked that down, that was tracked down to a financial stock newsletter. Now, obviously, they're trying to sell you on buying their newsletter for $99 a month is what they're trying to do. And inside there, they say, "Oh, we have this, special secret crystal thing, and if you give us $99, we'll tell you what stock that is." But it's all basically a scam. There is no such thing. So, you can't believe. Well, the thing is that these financial letters can say anything they want. They could say SpaceX is holding Martians, right? I can say that. I can say SpaceX is is holding Martian technology, but it wouldn't mean anything.
Yeah, but
right?
SpaceX is a reliable firm where the rockets go up and come down again and land.
SpaceX isn't a reliable firm, but I'm saying anybody can say anything about SpaceX. Like I could say SpaceX has rockets that don't use propulsion, but that would be a complete lie. So
SpaceX has its own information service, apparently, that you can get if you're computer savvy enough. You can get not from somebody writing about SpaceX, but from SpaceX company itself. And
no,
so
I'm as a skeptic, I basically say that you have been fooled by the internet. So not everything you hear about anything is true.
Would you be willing to take a look for me, for us? Would you be willing to take a look to see if SpaceX claims, not somebody else, but SpaceX claims that they have this spaceship under construction that does not use a rocket to get off? Could you check on that?
Yeah, we can do a quick internet search on that, and let's see whether there's anything with SpaceX and inertial propulsion. So SpaceX inertial. If I can spell inertia. Inertial propulsion rocket. Well, it wouldn't even be a rocket, but
Spaceship.
let's see here. Propulsion systems, propulsion reactionless drive, impossible EM engine, SpaceX.
Reactionless drive would be the one. Reactionless drive.
Reactionless drive. Let's see here. We have a reactionless drive, but there's now a SpaceX thing in here. You've got SpaceX, got the Merlin engine. Let's see here. The only thing, the mentions that we have here, SpaceX as being the conventional way of doing things. Let's see, advanced propulsion systems and possible EM drive. So the answer is no. I see nothing on the internet that's joining up any kind of inertial propulsion or reactionless drive with SpaceX. Let's see here. They have a thing that's directly involved. Has Elon Musk spoken about EM drive, which is what this is about, basically? Yeah, what you're saying.
Alistair has a comment. Look for propellantless.
Propellantless. Or without propellants or something. But I'm pretty positive on everything that I've learned about, know about SpaceX. And I kind of keep track of these guys. They've never said anything about that. They are strictly a chemical rockets, let's go into space company. And they would probably laugh at you if they thought they were doing something like that, I would think. Of course, that's only my own opinion, but like I said, I'm fairly savvy and in the know, and I would have to say that that is completely false. So I don't know where Bill's getting this information from, but Bill says a lot of things which I have a hard time believing, but that would be one of them. Not confirmed by anything that I can look at on the internet. Now, some of the things that Bill says, can be confirmed. If you talk about his early work in computers, you can go and you can look up, exactly the machine that he helped develop. And those are certainly true. But in this case, I don't think they can find any particular support for that. It just sounds like an internet rumor.
Search under SpaceX propulsion systems.
Well, let's see here. Alistair, he put a link here about, of course, I can't share this with you guys, but let me just take a quick look. Aerospace America, space tethers to demonstrate propellantless propulsion for deorbiting satellites. Now, this is something which I know it does actually exist, that you put a very, very large tether that you can basically grab a hold of the Earth's electromagnetic field and drive a satellite around. So that is an example of a propellantless method of propulsion, where you're basically taking advantage of the Earth's electromagnetic field to move yourself around. Or in general, you can use it to generate electricity. I mean, the last time they tried this, the tether charged up and immediately burnt out, and it was a disaster. But theoretically, if you were to put a big cable and you dropped it all the way to the Earth, there would be like, gigawatts worth of power coming out of that thing. Since there's a gigantic difference in electrical potential between between space and the Earth, which kind of shows that Earth is like a charged ball of some sort. That electricity is very much intimately involved with space. So, but that is one thing I do know about. That does happen. You can catch the magnetic drag. You can take advantage of the Earth's magnetic field. You can work against that. That can happen. So, but the thing that this does remind me though of is Bob Lazar's work, and he claims to have reverse engineered how UFOs worked. And he explained how the aliens are able to travel faster than the speed of light by using gravity. So he says that the way that all these ships work is mostly through gravity. On the bottom of the ships, they have like gravity projectors. And when they turn these things on, they create basically artificial gravity. And he says there's an A gravity and a B gravity. And it's like, he says, the Earth emits like the B gravity, and if your spaceship emits the B gravity, then you get a repelling effect. Just like, opposite charges, you get a repelling effect. And if you do A gravity, then it would attract, right? So they're saying that the reason why the UFOs kind of like hover like this, like they're kind of unstable, is because they're just balancing this beam of opposite gravity waves. And that's what keeps the UFO up. And if they want to go forward, they just alter the beam such that's a little bit weaker this way, so they fall into they basically fall in one direction, and that's how they move around. And but what he says about faster than light travel is that when a spaceship wants to travel faster than the speed of light, it points the bottom of the ship in the direction it wants to go. And then it cranks up these gravity generators, and like it becoming a massive black hole, these gravity generators generate so much gravity that they actually compress the region of space in front of them. So they would point it at Alpha Centauri, and then they would turn on their gravity beams. It would literally compress all the space between Alpha Centauri and the spaceship into a smaller area, a smaller distance. So take all the distance between the nearest star and the spaceship and compress it into like 1 yard worth of space. And then what you do is you just shove your spaceship across that 1 yard of space, that distance, and then you turn off your gravity generator, and kaboom, you are at Alpha Centauri. You didn't have to travel. You travel through, I don't know, the compressed space somehow. I'm not exactly sure how that would work, but somehow after you compress the space, then you can push your spaceship through that compressed space and then pop yourself out into a new bit of space, right? So let's see here. So Alistair says, asked this question about Bob Lazar. How did he know that the aliens were using element 115? How did he know it was 115 when 115 had never existed on Earth? Are we supposed to believe that the aliens call it element 115 in their alien spaceship diagrams that they conveniently had printed on paper, not stored electronically? Well, first of all, Bob Lazar knew there was element 115 because they had actual samples of it. They had these discs, and they could cut them, and they could measure them, and assuming that you have a sample of 115, which they did, then yes, you can tell that the atomic weight is 115. So that's how they knew they were using 115. And it did exist on the Earth. Apparently, it's very hard to make. It's not something you would naturally find in the Earth. And the aliens actually didn't provide diagrams to Bob Lazar. Bob Lazar's job was actually to reverse engineer these spaceships that were kind of ill-gotten. Apparently, we were having some treaty with the space aliens. But at some point, there was like this shootout, he says, and we shot up all the aliens, and there was nearly intergalactic war. But in the end, the aliens went back to their home planet, leaving behind these spaceships for us to try and figure out. So it's like we have like barely any information given to us from the aliens themselves. We have to sit there and figure it out. In fact, Bob Lazar's lament was that, why are they having me try to figure this out? He's just kind of a regular old guy. They should be having the smartest people in the world looking at this rather than hiding it away in some laboratory with some, rinky-dink researcher like myself, Bob Lazar, looking at it, right? So look up the half-life of 115 and tell me again about how they had samples. Well, once again, we don't even know what the half-life of 115 is. We've not conventionally, made it in the laboratory, and or maybe we have. And if we did, we know that the half-life is 0.6. Is it that long? 0.65 seconds? That's enormous. That couldn't possibly be seconds. That must be nanoseconds or attoseconds or something. It couldn't be close to half a second. Nothing that decays except for neutrons lasts that long. But it also depends on what isotope you made. The isotope that, if we managed to make it, and I actually have my own doubts whether we actually made it or we just found something that might have been that heavy. It's just like if you make something in the Hadron Collider, and the only way you can tell what they weigh is by the decay elements. Yeah, you could probably find something that corresponded to an elemental weight of 115, but or you could have that's just something that just randomly came out of the data, right? Because you can get an element weighing practically anything. You just have to cherry pick which ones you want to get the 115. But another personal story that I have about 115 is that I used to talk with this guy called Merlin. And Merlin himself claimed that he could transmute materials to make this 115 element. And in fact, he said he did create this 115 element, and it weighed, way more than lead or gold or anything else. And that when he sent it to a government lab, basically the sample never came back, right? And suddenly, cars with black vans started showing up at his place and stuff like that. So he claims, and you can look this up. If you look at 115, you'll find that there are transmutation recipes for actually creating things like gold and 115. So theoretically, you could make 115 in your garage, basically. Although I don't know that that any of that's true. I can only tell you what people have told me, or that the element 115 would be able to generate these gravity waves. I have a great doubt about that too, because I don't think we see that would be like a radical departure in the behavior of materials, because we don't see anything like that in any other material where it like affects the force of gravity or generates a force of gravity or anything like that. I would agree that perhaps that the 115 is a tremendous energy source, and that energy source was directed to the gravity generators, and it was the gravity generators themselves which created the gravitational force, I would say. So Alice just said, if you listen to what is claimed by the horse from the horse's mouth and not from what other people claim about what he claims. Yeah, there's claims about what he claims. So it's like, I don't think Bob Lazar actually figured out how the UFOs worked. I mean, probably his diagrams are accurate, basically, but I don't know. No, I mean, I've read Bob Lazar's story. I mean, of all the things that he was sure of, I think that was 115. He was pretty sure of that. And I think that chemically and physically and experimentally, that is something that we can know, that there was some mysterious substance that the aliens had given us. Of course, this could be a whole bunch of hooey from the get-go anyways, but I think that was probably one of the things that he was sure about. But I'm only bringing that up just in the context of warp drive, because that's, I think, a more practical way of making it work. If you can compress the space in front of your spaceship and then push yourself through the compressed space and then let go, that you can then travel faster than the speed of light. Yeah, Alice just pointed out he does not claim to have met the aliens, and he only had access to their tech. That's just all on a need-to-know basis, and he would hear stories, like the alien battle and how he ended up in possession of these spaceships that he could examine. Right? Basically, there was the aliens did not give us these spaceships. These spaceships were abandoned, and we're left to try and figure it out, which I don't think we did. Well, we do have things like the B-2 bomber, which has been said to use some of this technology because they electrically charge the skin of the B-2 bomber, which in my opinion is a way of reversing gravity. Since gravity is just like the positive electric field, so if you charge your plane positively, that will give you some lift. So, but the other thing I like about Bob Lazar's, what he was saying, that it could be complete hooey, but it also meshes nicely with, say, my own personal feelings and theories about what gravity is, which gravity is just an electric charge. It's just an electric charge. So you could have the A gravity, which is gravity created by a positive electric field, and B gravity, and gravity created by a negative electric field, and that would make sense. That you could have you could either repel or attract, or create a gravity gun, right? If gravity is just a wave. Yeah, I'll let you have last word here, Dennis. We're just about the end here.
Okay, you're talking about the B-2 bomber. I think you meant the B-1 bomber.
Oh yeah, the B.
But the B-field Brown effect is what powers it. And what happens is that the air is ionized at a negative part of the bomber's fuselage, and it's given a negative charge, and then it's attracted to the positive part of the B-1 bomber, and it crashes into it, giving it its momentum, and then stops being an ion. However, the B-field Brown effect, someone tried that in a vacuum, and there's no air in a vacuum, so it just didn't work. So the B-1 bomber works in the Earth's atmosphere, but it would not work in outer space.
But it still might work here in the atmosphere. Maybe that's why they use it. So Alistair has one other comment here, is that he's doubting that if they came across a element 115, that they would know they have it. And no, that's not true, because all you'd have to do is put it in a mass spectrometer and you would indeed find that the mass of that atom, which, I mean, this is something we know how to do. You make a gas of the atom, you put it in a spectrometer, you see how far it can go in its ionized state and be deflected, and you can calculate the mass of the atom that's in there. So that's certainly how we would tell that it was 115 or any other element. That's how we measure all atomic weights, right? We don't compare it against something else. It's like he was under scrutiny, couldn't complain to have dragged the mass spectrometer in his back pocket. Well, of course not. He has access to all the labs of the U.S. military. Of course, that would have been something that probably someone else determined before he even got there. That wasn't his job, really. His job was to figure out how the thing worked. He probably had to ask, "What is this?" And probably someone told him it was 115. Yeah. So I don't think the story necessarily breaks down there. There are a lot of places the story could break down, but probably not there. But we are at the end of our time. So just to summarize, the main topic was the topic of faster than speed of light. And I brought up this article from this NASA guy saying how this could possibly work and how it uses Einstein's relativity to manipulate space-time. And my opinion on all that was that, this had no more validity than the original Star Trek, right? Or anything that anyone could actually write about. Especially when they say that, well, it requires negative energy and more energy that can contain in the sun, and you could never do it. And it's like, that's not really practical. I mean, some people pointing out, well, given an experiment that would move us forward in this direction, and there is none. It is truly science fiction, is what I would say. And we did get into some discussions about relativity, and I think there was a fair amount of agreement that there probably is a preferred frame of reference. Dennis brought up these 5 experiments that point in that particular direction, that there is a fixed frame of reference. And that when you do have fixed frame of reference, then you don't have all of these paradoxical problems about your nose going faster than the speed of light and creating a black hole, right? Because you have a fixed frame of reference to judge everything by. But that would be the end for this episode of the John Chappell Natural Philosophy Society. And tell all your friends, and hope to see you here next week. So long.